All right, so welcome everyone. This will be our last lecture in the trigonometry course. We're going to be going over the last two sections in chapter 8. This is the last chapter that we will be covering. So just to remind ourselves, the Unit 4 test is the last unit test that will comprise of the chapters and our units in chapter 7 and chapter 8. And it looks like we're going to have some chapter 8 homework due coming around the end of the week. So if you guys didn't get a chance to watch the previous material on chapter 8, I encourage you guys to do that as well. But we're going to be jumping into section 8.3 to start. And this section is talking about some more properties with the trigonometric form of complex numbers. And so we're going to be going over really three operations in this section: quotient property, a product property, and a power property. And how do we combine complex numbers with those operations? So let's just walk through some definitions, and then we'll walk through some of the operations. Division and multiplication are actually pretty straightforward, but we'll need to take some time on the what we'll call the power rule, but it'll have another name to it. So let's walk through first the multiplication theorem. So this is for the trigonometric form working with multiplication. Just to remind ourselves again, the form of a complex number is some complex number z, we'll call this z1, is r1 times cosine theta sub 1 plus I sine theta sub 1. And those subscripts are just to distinguish between the second complex number we'll call z2. So all complex numbers in trigonometric form will have that format. So if we have two complex numbers of the same form there, just different values, then we can take their product and we'll call that z1 times z2. And what we'll end up doing is we'll take the product of what we'll call the modulus. So this is the product of the modulus. And then we will take the sum of what we call the argument. The sum of the argument. So it's not necessarily a complex process there, but we do want to take those two operations when we're working with the multiplication. So it's kind of feels a little similar to when we're working with logarithms. If you remember some logarithm properties, I try to liken it to that in terms of just the thought process of combining these complex numbers. So let's take a look at a couple examples and kind of walk them through in terms of their multiplication. So we have two complex numbers. If I were to multiply these two complex numbers together, what would be my new modulus? If we're looking at A. Right, so we're going to take the product 5 and 2. You're right, that would be giving us 10. So we take the product 5 and 2. That would give us a 10 for the modulus. And then we'll have a cosine of some angle plus I sine of some other angle. And what would be the argument, in other words, the angle that's produced from this complex number? looked at our definition again. Yep, I think, Kevin, you got it. So 30, or close, not quite 30. We have 15 and 25. 40, right. Yep, because we're just going to add the two angles together. So 15 plus 25 is going to be 40. So this would be the new complex number in trigonometric form. So 10 cosine 40 plus I sine 40. No problem. Right. Okay, so let's take a look at another one. Same multiplication here. What would be my modulus for our part B? We have a modulus of 9 and modulus of 7. We want to multiply those two to get started. That would be 3. That would be correct. And then we'll take our form of cosine plus I sine. And what would be our new argument here? We add those two angles, 225 and 45. Looks like, yep, 270. I think you got it there, Anya. 270. So if we add those two angles, we get 270. And just to remind ourselves, this complex number, or in trigonometric form, always has the same argument in each position there. So you're never going to have like cosine of 90 plus I sine of 180. So it's always the same angle applied to both the cosine and the sine in your complex number. So that would be our new one. All right. Any questions with the trigonometric form with multiplication? So we can also do some conversions here and work with the standard form. So if I have a complex number, call it 2i, and another complex number we'll call negative 5i, we can consider what the product would be here. One thing that we might want to do here, and in this direction, we don't necessarily have to do this every time, but it might be helpful to convert this to a trigonometric form and then multiply. So we're going to try that method, and then we'll actually go in both directions so we can confirm our solution. But we'll do this. We'll convert a complex number to trigonometric form, and then we'll multiply. So two things that we'll do here in part A. So to think about converting these to complex, or the trigonometric form, let's just see if we can graph these two complex numbers, and then we'll try to write them in the trigonometric form. So we're going to start with the Z1. So how would I write the value 2i on our graph? Where would that belong? If somebody wants to mic up and explain that. Where would we find 2i?
It's going to be on the imaginary axis, which is what.
Yep, exactly.
It's going to be 2, or up 2.
So our imaginary axis is our y, our real axis is our x. So it's 2 units up on our imaginary axis. Very good. That was Annabelle on the mic. Nice work. So we'll call that 2 units up on the imaginary axis. That looks great. So that's Z1. How about negative 5i? Where would we go for that one?
So now you're just going to go down, obviously, because it's negative. So down 5i.
Yeah, excellent. Yep. So we're going to be on the negative y-axis 5 units. We'll just make that a little longer. We'll call that negative 5. Very good. Nice work, Annabelle. So now let's, with those graphs, now we can kind of consider what we have in terms of a trigonometric form. So let's start with the first Z1. So the Z1, we'll rewrite here. Well, the modulus, if we consider writing in trigonometric form, we have r cosine theta plus I sine theta. That's our general trigonometric form. So what would be the modulus for that Z1? What would be in place of r? What is the distance from the origin? Yep, Kevin, you got it. 2. Yep, we'd have a modulus of 2. It's just got a distance of 2 from the origin. And then what would be the angle that's made by that vector 2i coming out from the origin? What's the angle that's created? Yeah, Sam, you got, yep, 90 degrees, right? So this angle right here, we just made a 90-degree angle with the positive x-axis. So that would be 90 degrees. And plus I sine of 90 degrees. Excellent. So there's my first complex number. We can rewrite the second complex number. We'll call this one Z2. Well, with those same properties there, we want to have a modulus. In this case, our modulus for the green vector has to be 5, right? We're 5 units from the origin. And in the direction of, we looked at our angle that's created here. What's that angle that goes and wraps around to that green vector? Yep, 270. Excellent. So that's a 270. So cosine 270 plus I sine 270. Excellent. All right, and now that we got them in complex or the trigonometric form now, we can consider, let's just do our multiplication and see what we got. So in this case, we'll have Z1 times Z2. We have the moduluses of 2 and 5, so we can bring that to 10. Very good. And then what's my new argument? Yep, add the angles. So if we add those angles, that is 360. Oops, 360. Now, if we'd like to go one step further, what is the cosine of 360? I think we know that. That's the same as really 0. So the cosine of 0.
1.
Cosine of 0 is 1. What about the sine of 0? say 0 degrees. This is the point 1 comma 0. So our sine happens to be, 0. Excellent. So it's really boiled down to 1 plus I times 0 times 10, which here is just going to be 10 times 1, or 10. So that whole product there just becomes 10. Now, just to confirm this is just another way you can work with these complex numbers. Is in this case, it's probably even easier to just do the product with the complex numbers themselves. So if we try that, we can say that z1 times z2, that's going to be 2i times negative 5i. So we could go for just multiplying these two complex numbers. So we have two constants, 5 and negative, or 2 and negative 5 would be negative 10, and then I squared. And what is the value for I squared? We're looking at our complex or an imaginary unit. I squared. Yep, I squared would be negative 1, right? So we got negative 10 times negative 1, which in fact gives us 10. So either way we go about it in this problem, and really every problem, if we do the algebra correctly, we'll get back to the same solution. I did want to go through this side of things just to kind of walk through how we convert those complex numbers again. But you certainly can go through either way, multiply the trigonometric form or the standard form of the complex number. So let me pause here. Is there any questions with that conversion? All right. So we'll keep it rolling here. So the next conversion here, we certainly can multiply these complex numbers as is. Let's take maybe a different method and just go for multiplying these complex numbers in the standard form, just to remind ourselves how that works. So if I wanted to go and find z1 times z2, in this case, we kind of have really some binomials, since we have an imaginary piece and a real piece for each of these. So let's just line them up. We have 4 minus 3i times z2 is 1 plus I times the square root of 3.
Mr. Coughlin?
Yeah.
I was going to ask, couldn't you, since it's a rad 3, could you just square it to break it off from the rad 3, just to like get rid of it essentially, and then just from there do your basic algebra, right?
So for right now, so this rad 3 that I just wrote.
Yeah, it's in the problem, like 1 plus I rad 3. Could you square that rad 3 just to get rid of like that little rad sign, I guess? So it's just 1 plus 3.
So if I square that portion, I'm changing the number. So I don't want to change the number. I just want to take what's there and do my operation with the other complex number.
Yes, sir.
Yeah. So we will do some multiplication, but we can't just, square something just, I guess, necessarily because we don't like the look of it in the problem. So that can cause some problems. So we're just going to want to apply the multiplication operation on these two. And so let's just consider what that would look like. It's really going to look like, a binomial multiplication, which would look like kind of a foiling technique. So just like a foiling technique, I'm going to consider some products. So 4 times 1 would give me 4. And certainly we're going to have some simplification afterwards, but let's kind of walk through each of the components. The next component we would have looks like 4i and then a square root of 3. And then we'll have a couple components multiplying with a negative 3i. So negative 3i times 1. And then we'll have a I product here in the last portion. So we'll have negative 3i times 1. Negative 3i. And then the last product there looks like we have negative, and we'll have I squared square root of 3. So there's certainly some simplification we can do here. The first simplification we can consider is looking at that I squared again. So remember, I squared is always negative 1. So this is always negative 1 there with the I squared. So we can rewrite this one time with 4 plus 4i squared to 3 minus 3i. And then if that I squared is just a negative 1, we can say that's just a plus 3 square roots of 3. So that would be one simplification. Turn that to a positive. To make this look like, I guess, a complex number form, remember our complex numbers usually are in the form of a plus bi. This looks like a little more complex than that, so let's just reorganize these terms a little bit. So I'm going to want to collect all the real pieces in the front. So we can say 4 is real, and then our 3 square roots of 3 is a real piece. So we have 4 plus 3 roots of 3. That's the real piece. That's kind of playing the role of A over there. And then we have a complex piece. So I'm going to rewrite that complex piece. We'll do that in red as well. So we have 4 square roots of 3 times I. So 4 square roots of 3 and a minus 3, and that's all times I. So if you consider pulling out that I out of the grouping in the middle, we would have a complex piece, and that's in red is kind of playing the role of your B value in front of I. So take a minute to soak that in, see if all that lines up for you guys. So this would be the simplification in a standard form there, just to look at that product. So again, this is working with the complex number in the form of A plus B I. Any questions with the product property before we take a look at some division? Okay, so the next property, the second of really 3 main properties we'll take a look at in this section, is the division theorem. So again, we're going to be starting off with two complex numbers. We'll call them Z1 and Z2, just the same as before. And now we're going to take the quotient of Z1 and Z2. And let's just take a look at what the operations unfold. We will take the quotient of the modulus, and then we have the difference of the argument. There we go. Difference of the argument. So again, it feels very similar in a sense to the logarithm properties when we're doing logarithms. Division translates to subtraction of logarithm pieces. So kind of similar in that sense, but definitely a different concept, but you can kind of pair those in your mind if you want. So let's consider just a few in our trigonometric form first, and then we'll look at the standard form together. So if I consider the first example, I have 18 as a modulus and 12 as a modulus. So do the division there. I do want to keep this kind of in terms of a fraction. So that is a 3-to-2 ratio. Anya, you got that. So we do have a 3-to-2 ratio on our modulus. And then what would be our argument for our angle here? Yep, so we take 51 minus 32, that would give us 19. So 19 degrees will be our new argument. And we could leave it just like that. That would work well. So 3/2. You could rewrite it as 1.5 in the front if you'd like when you enter it. I think that would be acceptable since that terminates and doesn't repeat as a decimal. To look at the part B, what would be our new modulus? We have a 7 and a 21. Again, we can try to reduce those. That would be to a 1/3 ratio. That looks great. And then how about our argument? Anybody new want to throw out the argument? Would that have to be?
Would it be 47, Mr. Copeland? So we cos 47 plus sin 47?
47. Yeah.
Because 120 minus 73?
Yep, that looks good. Yep, 47. So 120, and we'll subtract the 73. That looks great. Excellent job. So cosine, make sure we have that parenthesis there, cosine of 47 plus I sine of 47. Excellent work. All right. So that's just our trigonometric form. That makes that property makes it nice and to do that. Now we're going to go into division with our standard form. Now this is going to take a little bit of a different technique. And I'd like to kind of do this technique kind of with the standard form. You certainly can convert this, and kind of giving you a direction to here in the I'm actually going to just go for keeping in standard form here, just to give you guys exposure to this technique. And maybe we'll do the conversion for part B, and we'll just do the straight multiple or the division for A. So if I was going for Z1 divide by Z2, so the quotient of those complex numbers that we have here, well, I'm going to line these up just like they are. So that would be Z1 is -1 plus I square root of 3 in the numerator. And then Z2 I'll place in my denominator. So just like I would with a division. And now this probably looks kind of similar to something that you guys were working on in the first couple sections. This just looks like dividing, doing some operations with the imaginary unit. Now, if you were exposed to something like this, what would be your guys' first move to try to evaluate this quotient from your experience in the last couple sections? Okay, so invert denominator. What is meant by that? Do you want to flesh that out? Okay, yep, we do want to rationalize the denominator, and I think there's a conjugate. Yeah,
Sorry,
excellent.
I
Yeah,
totally
all
blanked
those.
at the name for a second.
Nope,
Like,
you're good. You're good. Yeah, conjugate, and that's going to help us rationalize the denominator. So you guys are all on the same track. We're just getting our kind of terminology in order, which is perfect. So what would be the conjugate that we want to use in this specific problem? What do we want to use for the conjugate?
square root 3 minus I?
Yeah, there we go. Yeah, so we want to use a conjugate. Long mathy term that just means kind of the, really the opposite sign on a binomial. So we'd want a square root 3 minus I, that's the conjugate of that denominator. And we want to multiply by that on the top and the bottom.
You have to be careful. You have to be careful too, because you only want to do the second letter or symbol or whatever, not both of them. You don't want to switch both of them. So if it's a positive up front, you leave it alone, or a negative or whatever. I didn't realize that. I'm like, oops. I'm gonna look back at my notes.
Yeah, so we just want to switch the sign in between. That's correct. So we don't want to negate the whole thing. Yeah, so if we put a minus sign in front of the square root of 3, we just have the opposite. So we just want the conjugate. Good point. Okay, so now let's consider, really it's a multiplication problem after this. We want to multiply this conjugate in the top, or the numerator and the denominator. So let's consider walking through that. So the denominator, and again, after we go through kind of both methods, once we go for part B, you can certainly choose kind of what method you like the best, but we'll go through this one first. If I was multiplying conjugates here in the denominator, we'll start there. Well, conjugates have a nice property where we can just take their difference of squares and subtract them. Well, that's the difference of squares, is subtracting the square of both items. So we're going to square the square root of 3. That would be 3. And then we'll subtract that with the square of the last item, which is I. So that would be I squared. So conjugate pairs brings difference of squares. That's kind of a little motto or a catchphrase. conjugate pairs give difference of squares. All right. So there's our denominator there. We just want to square both items, subtract them from one another. And now we need to do a kind of a foiling on the numerator. So we do have some foiling to do here in that numerator. So we have the product with -1, 1 of 3. So that'll be -1 square roots of 3. -1 times -I, so that'll be just a plus I. If I did my next product, what would be the next product that I would have to do? So the inner terms here, I did that inner term, I would have positive I squared to 3 times square root of 3. So that's just going to be 3 and an I, 3I. Excellent. And then how about the last term, if we do the last product? Yeah, so we have -I squared, and then we also have that square root of 3 hanging around. So we've got all the items right there. 3I and then -I squared, square roots of 3. Okay, cool. So we still got a little bit of work to do, but we're chugging along here pretty well. So let's take a minute to consider the simplification for this. We can recall that I squared again, that's our -1. So this goes to -1. And then we can also have a -1 down here. So the I squared property comes up 2 times in this quotient. So if I were to rewrite this numerator, what is the real piece in that numerator? What do we have left? I think you might be right, 0. Notice that we have negative square root of 3, and then we'll have a negative square root of 3. So this will actually turn to a positive square root of 3 here with that product. And so those will actually cancel. I'll just be left with 0. All right, that looks good. And then our imaginary piece, I and 3I give me exactly 4I, right? So I'll have 4I in the numerator. And then we can look back on our denominator here, 1 minus -1. That'll give us a double negative, a plus, and that will also give us 4. So when we sum that up, looks like we're just going to get an imaginary piece, 4I over 4. I think that's just going to be I. So all that work, and we just end with I. And that would be our final result there. The multiplication of those complex numbers. Now, we'll go through a second kind of method to do this kind of same thing away from those conjugates, but let me pause here and make sure that You guys have a view of this. Is there any questions I can answer with part A there? Okay, so we'll probably have to pick up the pace just a little bit in this last portion, but if there is questions, happy to answer them. So in this part B, I'm going to actually convert them to a trigonometric form, and then we'll use the property that we just learned up here. So for in standard form, I'm going to first convert to trigonometric form. And then we will do our quotient. So if I rewrote these and just put a little graph on each of these complex numbers, I have 1 plus I. So 1 plus I is in the first quadrant. That would be 1 unit to the right and 1 unit up. So it would be kind of a direct 45, where I'm I units up, 1 unit to the right. Notice that in this case, this vector creates a 1 by 1 plus square root of 2 triangle here with that vector. This is Z1. And that argument there, that angle that's produced, this is a 45, 45, 90 triangle. So this would be an argument of 45 degrees. So here we can say that Z1, kind of a quick conversion here, is the square root of 2, and then times the cosine of 45 plus I sine of 45. There's our argument. We can also go and try to convert the Z2. I'll do that in a different color. We'll do that in red. For I, that's something similar to what we saw before. That would be just 4 units up on our positive y-axis, 4 units, 4i. So Z2, we could say that's got a modulus of 4. And what would be the argument for Z2? Argument would be, yep, very good, 90 degrees. And there we go. So if I go for my quotient Z1 over Z2, I can do that pretty quickly here. Z1 over Z2. We get our square root of 2 over 4 as our new modulus, just the quotient of those. Notice that my square root's not in the denominator, so I don't necessarily have to rationalize. There's nothing to rationalize. It's just kind of what it is there. And if I take the difference in my arguments, I get cosine of negative 45 plus I sine of negative 45. And just to kind of create, and this, usually is the case for most of the inputs, we usually don't want to have that argument be negative, so we can convert that to its positive coterminal angle, which would be a 315 degree angle. So we could rewrite that value as 315. So that would be.
Mr. Coughlin, how did you get 315 from negative 45? Did you subtract 360 from both of them?
Add 360.
Or add 360, yes.
Yep. So it's the same angle. It's just the positive angle going around. So it's the equivalent angle, but it's just not negative. All right, so that would be our quotient property. All right, so let's, we might not finish the next law or the theorem before we break, but we'll at least introduce it. And you can take kind of either of these methods to work through, depending on what they want as your final result is kind of the determining factor. So they'll show if they want their solution in the trigonometric form or the standard form. All right, so this last one is kind of a power rule. It's called de Moivre's theorem. So de Moivre's theorem. And this is kind of again, a power rule, because we're going to be taking this complex number and we're going to be raising it to some n power. And when we take the complex number and raise it to a power, this is kind of what the items are. And I do believe he is a French mathematician. That is correct. de Moivre. I was that. I don't think I've confirmed that lately, but I think that is a French guy. So we can take a look at what these operations are going to look like inside. We are going to take our modulus and we're just going to raise it to that power, so r to the n. And we're going to actually multiply our argument by the power. Again, this is kind of similar again to a power rule in the logarithm cases. So raise our modulus to the n power and then multiply by the power in our argument. Great. Okay. Got a nice bio there in the chat. Thank you. Yep. Excellent job. So just as an example here, when n is equal to 2, we have a kind of example of what this would look like. Your new complex number is going to have the form r squared cosine 2 theta plus I sine 2 theta. And so you can tend to kind of see how the pattern works with an actual example there. So let's consider how we would go about working with this theorem with a single example, and then we'll kind of look at that complex example down in part B, maybe after the break. So the first thing we need to do is actually get this complex number into trigonometric form. So we first need to convert this. So we're going to try to convert this complex number. And so to do that, I'm going to draw this out a little bit and see if I can find its modulus and its argument. So we have -2 and 2i in the center. So I'm going to just try to replicate that vector that we're cubing here. So if I try to replicate that, that's going to be -2 in my x direction, and then +2 in my y. And vector going to be coming out over here in the second quadrant out of 45. So we can consider first, what would be our modulus for that vector? If this was a 2 by 2. Mm-hmm. 2 square roots of 2. Yep, I would agree with that. So here we'd have and I'll call this z for right now. This is 2 square roots of 2. Cosine, what is our argument for that same vector? What is the angle formed here? So the reference is 45. So this is 45, 45, but we are in the second quadrant. So we are looking for this angle right here. That's going to be our theta for that vector. So 3 pi over 4, or we do want to keep this in terms of degrees. So we'll just end up with 135. So 135 will work. So this is 135 working it in that second quadrant. So we have 135 degrees plus I sine of, again, 135 degrees. Okay, so that is the actual complex number that we're working with, but we do want to cube this. So that's, really that complex number sitting right there. We would like to go out and find this complex number cubed. So we're really finding z cubed in this problem. We'd like to cube this. So if I'm going to cube this with our properties, let's just write it out in longhand first. I want to cube the modulus. So I'm going to take the modulus, and we're going to cube that. And then I'm going to have a multiple of 3 for my argument. So that would be 3 times 135 I sine of 3 times 135. So there's really, again, 2 operations in Dumov's theorem, one with the argument and one with that modulus. All right, so let's work through the cubing first. If I wanted to cube 2 square roots of 3, or 2 square roots of 2, I cube both of these components. So if I cube the positive 2, that would be 8. And if I go to cube the square root of 2, well, squaring the square root of 2 would be 2, but then I have another square root of 2, so that would be really 2 square roots of 2 if I cube that portion. Certainly we can do one more multiplication there in another line, but we'll finish that. Cosine, what would be my new argument? 3 times 135. $405, yeah. So that's 405 degrees. And so there's a couple of simplifications actually I can do here. One is kind of work with that modulus one more time. That's going to be 16 square roots of 2. And then we'll have here cosine. If I looked at what would be a coterminal angle in our unit circle to 405, what would be the equivalent angle that we're working with there? I found a coterminal angle to that. Yeah, Sam, you're right on. Yep. Anya, 45 degrees. Right. So I subtracted 360 degrees to get a coterminal angle to 140 or 405. That would be a 45-degree angle. So I'm going to use that in my final answer. And that will do the job right there. So that there's my complete solution there, if we wanted to leave it in complex form there, or in trigonometric form for the complex number. Alrighty. So it looks like a good time to take a break, 9 o'clock. So we'll take a 5-minute break here, come back at 9:05, and we will roll on to the next example. I'll try to set the table a little bit for you guys as the break rolls on here, but we will walk through each step of this part B, and then we have one more section working with complex roots. So give you guys a few minutes to switch out and break from the screen. All right, so let's begin again here with part B, working with Dumas' theorem. We have 3 complex numbers in this operation. We have really a product and then a division or quotient to work with. And so we're going to try to break down each of these components. There's really 3 components in this problem. We'll try to convert these to our complex trigonometric form, and then use our all really 3 properties, the division, quotient, or the product, the quotient, and the Dumas theorem to work with these. So I have the first complex number written out here. We'll call this one Z1, the top left. That's 2 plus 2i. And we have that written out. We have a modulus of 2 square roots of 2. And then that argument would be a 45-degree angle. All right. So let's see if we can draw out the rest of these, and then we'll kind of walk through taking the each property as we go as well. So if I wanted to finish off, I really want Z1 here is going to be raised to the 5th power. So if we take a look, this Z1 is going to be raised to the 5th power. So that's the first operation I really want to work with here. So very similar to what I did in the first example, I want to raise this to the 5th. So let's take a look at walking through that. So I have 2 square root of 2. I want to raise to the 5th. And then I want to multiply my argument by 5. So I have a multiple there with my argument. So let's see if we can simplify this one step and make sure that we have this ready to go before we move on to the next piece. If you considered multiplying through with the power of 5 here, 2 to the power 5 is going to give you 32. And then if you did square root 2 raised to the power 5, that should give you 4 roots of 2. And so we just need to multiply those two items together. That'll end up just being 128 square root of 2. So that's your new modulus on the complex number raised to the 5th. And what would be our new argument, that new angle inside cosine sine? I took 45 times 5. What would we end up with as our new angle? Mm-hmm. 225. 220. There is our z1 to the 5th. So we'll leave that there. And now I will try to work with the next one. So the next one we're going to be looking at is, we'll call this one z2. And that's the negative 3 plus 3i. So let's draw this one out as well. And I'll just draw these up on the top so we have them referenced at the beginning. So negative 3 and 3i, that means that we're in the second quadrant again, negative 3 and 3i. So again, we have kind of a 45-degree angle working here. So a couple of things we can note here. Our modulus now is just going to be 3 roots of 2 for that complex number. And again, our angle is going to be really similar to what we had in our last section. That's a 135-degree angle for our argument. So let me write this one in blue down below for Z2. We'll have Z2. It's going to be equal to, we have 3 roots of 2. And then our argument is 135. So we'll write this as cosine 135 plus I sine 135. Okay, so notice that in our problem here, we want to raise this to the 3rd power. So let's consider doing that next. So you want to raise that z squared to the 3rd power. So we'll raise each of these components. So we're raising this to the 3rd. And then we'll have a multiple of 3 in the argument. Okay. So how is this going to change our modulus? I'll let you guys write this down. It's a little bit of writing here. Get started. How can we think about multiplying or raising that modulus to the third power? Okay, we have 54 square root of 2. I think that would be correct. Let's think through that just a minute. I know 3 cubed is going to be 27. And then if you take the square root of 2 and cube that portion, that is 2 roots of 2. So if you multiply those together, you do end up getting 54 roots of 2. And then what would be our new argument here? New argument 405 or 45. We can keep it as a 405 for now. I think that would be okay. There's no harm in that. So we'll just keep it as our 405. Oh, we can take, I guess this is 4. Yeah, it's okay to do that. So let's go reduce. So that is a 405-degree angle. The equivalent is going to be a 45-degree angle to take a coterminal. So yeah, let's just use the 45. I think that'll maybe make it cleaner to just get started with it. 45 plus I sine of 45. That'll work. All right, so we have 2 of our components here. So we're looking really good. As we go through this, I think we could probably do one more step here, and I'll send another color here. We do want to take the product of these 2 items here. That's part of our problem is I want to take the product of z1 to the 5th and z2 to the 3rd. Those 2 things, that's what's playing in my numerator here. So might be helpful to just kind of, as we're walking through, let's just take the product of those 2 items as we go here. So if I take the product of those 2 items that are boxed here, what would be my modulus when I multiply those 2 items? So this would be my z1 to the 5th times z2 to the 3rd. I wanted to multiply those. Yeah.
Now my question is, how did you get 54 rad 2 on the z on the second box one?
Right. Yeah. So if I take this cubed, so I'm doing 3 cubed, that's 27.
Yes, sir.
And then I'm going to cube square root of 2. And so if I cube square root of 2, that's going to give me 2 roots of 2.
Okay.
And then I multiply those 2 things.
Yes.
So that gives me 54 and then root of 2. All right, so if I go next and just multiply our modulus here, so this modulus and this modulus, what do we end up getting for those 2 items there if we take their product? I think this should come out as a whole number. Yep, I think that would be correct. I think we should end up getting 13,824. That would look good. And if I looked at the modulus and I multiplied with those modulus, adding, we got 125 and 45, what would be my new modulus on this? $270, excellent. So 270. All right, and I'm just going to leave that just as it is here because I have one more operation with the quotient up. So let's turn our attention to the last component here. Is there any questions so far? Try to walk through this as slow as we need to, but we do want to get it done. So we have the whole numerator set. Now I just need to convert the denominator and take the quotient. So we're going to be looking at the denominator. So I'll do that one in green. So square root of 3 plus I. That would be square root of 3 in my x-axis and I in my y-axis. Show both here. So this ends up being, let's just draw it bigger. I might draw it on the other side. Let's draw it over here. So this last component, we have square root 3 and I. So really this is 1 and square root 3 for this triangle. So we really have sitting here 30, 60, 90. This is 1 square root 3, and that would be 2. So we do have a modulus of 2 in this one, the last component. And what would be our angle that's in that first quadrant here for that 30, 60, 90? Is that the 30 or the 60-degree angle? Right, yep, this would be the 30-degree angle. So that's a 30, 60, 90 triangle with 2 square root of 3 and I. So we do have a 30-degree argument and 2 as our modulus. So let's write that down. This is going to be Z3. We have 2 cosine 30 plus I sine 30. So that's our last component. And we are going to raise that to the 10th power. So right in our problem statement, we're going to raise that to the 10th, and then we're going to do our quotient. So raise this to a 10th. We have z to the 3rd to the 10th. Notice if I just multiply by 10 inside, this 30-degree angle is just going to create a 300-degree angle. So this will just be 300. And if we take 2 raised to the 10th power, what do we end up getting for that modulus? 2 to the 10th power. Yep, that would be 1024. Excellent. So we've got our last complex number all ready to go. That one was not too bad. Now we get to do our last step, which is just the quotient of a few items. So let me write this whole item out. So our final result, we're going to be taking the quotient between 13,824 cosine 270 plus I sine 270. Divide that by 1024 cosine 300 plus I sine 300. All right, so this is what we're down to, one quotient. If we take a look at what the new modulus is going to be, what do we end up getting for that modulus when we divide the constants on the outside? Excellent. 27 over 2, we can really call that 13.5 if you like. We could say that's 13.5, 27 over 2 if you prefer. If I do the angle here, notice if I do a subtraction of angles, that's going to be cosine of negative 30 degrees. What's the equivalent angle that's coterminal to negative 30 degrees? That would be, yeah, equivalent to 330. So in these problems, I always want to finish with a positive angle. So let's try working with that positive angle, 330. So I'm going to just change that to a 330-degree angle. And that's going to be it. We will seal the deal with that one. So I have to have those. There we go. And that is the final answer. So we endured that one. I do want to expose you to you guys to this one because you'll have to do something similar to this. Probably not this complex, but you'll have to be doing some of these problems that have multiple operations like this. So just to expose you guys to that. All right, is there any questions? I'll try to pause here for a moment or two. There's questions to talk about in this last problem. I don't think there's necessarily this on the final. I wouldn't expect that just because of the time. But I think there might be maybe a homework problem that has something similar to this. Again, not this complex, but it does combine the operations. So just wanted to expose you to one that combines the operations. You're certainly not going to have this on the final, like that problem. No. But I would expect something similar to part A. You know, part A, that's definitely available on the final, but probably, definitely not part B. So 330-degree angle came from 270 minus 300. That gave us negative 30. And then the coterminal angle to that is 330. So we're going to use the positive coterminal angle if we add 360 to that. Good question. All right, so let's take a look at the last section. Last section 8.4 is going to be looking at roots. So we'll dive into this, the root theorem. It doesn't have a fancy mathematician associated with it. So we're going to be talking about complex roots. And so initially, this is going to look a little more complex than I think it is. So we'll try to walk through that, first example really slowly. So the nth roots of the complex number, again, we're going to have a complex number in the form z equals r cosine theta plus I sine theta, are given in the form, we'll call this wk, which is the first root, equals r raised to the 1 over n power times cosine of theta plus 360k over n, and then same with plus I. Oops, this should be a sine. I don't know why that didn't adjust, but that is a sine. I sine theta plus 360k over n. So there's a lot going on here, so we're going to pull this apart and walk through exactly what we need from this equation. So one note is we're always going to have 2 square roots. There's always going to be 3 cube roots, 4th roots, and so on. Okay, so if we're asked for square roots, we're always going to have 2 solutions. If we're asked for cube roots, we're going to get 3 solutions, and so on. So let's take a look at the first example, and we'll walk through how to use this formula. So we want to find the 2 square roots. So we're getting solutions of our complex number. So the first thing that we're going to want to consider here is this value k is going to go from 0 up to the number of solutions that we want. So we're going to have 2 cases. We're going to have when k, this counter, is going to be set equal to 0 first. We're always going to start there. And then we'll have a case where we have k equals 1. So we're going to start with the k equals 0 case. And in this case, since we are taking a square root, that means that n is the value of 2. So n is always the number of roots that we're taking. So in this case, n is 2, and we're going to count the k's from 0 up into 1 minus that value. So filling in kind of the details of our formula, knowing those 2 counters. So n is always the root number, and then we're going to start with k equals 0. So this would say that we're going to start with finding w sub 0. This is going to be our first root. This is going to be equal to our original r, and I'm going to walk through that formula. R is 16. And then we're going to raise to the 1 over n. So this would be raised to the 1 over 2, or the 1/2 power. That's, in other words, a square root. And then we're going to go into our regular formula. This is going to be, and then we're going to start with beta, which is just 60. So this would be 60 plus 360 times k. K is 0 here. And then divide by n, which happens to be 2. So we're just following this formula right up here. I'll pause here to look at that cosine. So we're doing cosine of our angle plus 360 times k. In this case, k happens to be 0 to start. And then we're always dividing by the index of our root, which happens to be 2 here. And so that's going to repeat for the sine as well. We'll have plus I sine of that same arrangement. So that would be 60 plus 360 0 over 2. So this has maybe just a little simplification to do to find our first root. So the square root of 16, or 16 to the 1/2 power, will give us 4. And then if we consider the arguments here, 0 times 360, that just gives us 0 in both cases. And 60 divided by 2, that's going to be 30 degrees. So we'll be left with cosine of 30. And then plus I sine of 30. So there is one of the roots there. We have one of the two square roots for that trigonometric form. So looking back at our formula, and I apologize for the typo on that one. Try to maybe wipe that out. Just a line there. Are there any questions I can answer with connecting that formula for the first time?
So the something of the root means it's just the solution, like how many solutions you should be expecting?
Yeah, so the
Okay.
square root means that we're going to have two solutions, right? There's always going to be two square roots.
And just to recall it, k is less than what exactly again?
So k always starts at 0, and then we'll go up to 1 if we're taking a square root. So the next one we'll do, we're kind of halfway through the problem here, but we will do just a k equals 1 case, and that'll be done after that.
Okay, so it's the whatever, it's one less from whatever root you have.
Right, exactly.
Okay.
That's what it'll end up being. Yep. So,
I'm just trying to make sure I
but it'll
remembered everything
always,
correctly.
if you consider it always starts at 0, and then you're going to be doing n number of them. In this case, n is 2. So let's just take a look at how the formula changes with k equals 1. The only thing really that changes is that counter in the argument. So let's consider that. So w sub 1 is going to be, again, 16 to the 1/2 power. We're really going to copy our first result other than the k numerator. So we have cosine of 60 plus 360 really times 1 divided by 2, and then plus I sine, and that's 60 plus 360 times 1 by 2. So yep, this section is included. So we'll want to know things from this section. So let's walk through this one. We'll simplify this. This will be, again, modulus of 4. And then we will have the cosine. If I do 360 plus 60, that ends up being in the numerator. Looks like 420. And then we want to divide by 2. So 420 divided by 2 is going to be 210. We'll have 210 for that angle, or the argument. So those will be our square roots right there. And that's going to be the final results for those. So this is not necessarily the only way you can find the roots here, because we'll take a look at a couple of other cases where you can use some more algebra techniques. Certainly you can convert that to a standard complex number and then work with it. But this is one of the methods you can use. Let's take a look at the next problem here. If I want to find, again, just of a constant number, find the cube roots, or the 3 cube roots of negative 27, here's how I would probably approach this. One way is just to consider it in a equation. So if we had negative 27, well, if I want a cubed root, I really want something kind of cubed. And so one way I could walk through this is saying, what if we had an equation, x cubed is equal to 27, or negative 27, right? And I would like to solve for x. That's really what it's asking, is if I want a cube root, I'd like to know some value that's the cube root of negative 27. So I really want to solve this equation right here. So let's consider adding that 27 to both sides. Have x cubed plus 27 equals 0. And we'll notice that this is really a sum of cubes here. And so if you think back to kind of our algebra, there is a way to factor this that we can consider. This does factor as x plus 3. And then we'd have x squared minus that same 3x, and then plus 9 equal to 0. So if kind of the cubing factoring here, and I'll write it in general on the right side if you want to have this in your notes. If I have a cubed plus some b cubed, the factoring for this is just a plus b, and then a squared minus ab plus b squared. So that's the factoring for a sum of cubes, if you want to have that in your notes. So from this stage, we do have a couple solutions that we can grab. And one solution we might need to do using a quadratic formula here. So one solution, it looks like we can find that as -3, and we'll add that to the list. But we'll try to see if we can factor this portion first using a quadratic formula for that root. So we know that x here is going to be equal to, with our quadratic formula, x is equal to -b plus or minus the square root of b minus 4ac all over 2a. We'll have to apply that. So here our b is -3, so we'll have plus 3, and then plus or minus b squared is -3 quantity squared minus 4, a is 1, and then our c is going to be 9 here. And divide by 2 times a, which is still going to be 2 times 1. So we can work out the rest by just simplifying this expression. So we have 3 plus or minus. If we take a look at the square root here, what numbers do we find in the square root when we're done? Square root of -27? Yeah. And then that's going to be divided by 2. If we summarize that square root, -27. If we use a little bit of algebra here, we can reduce that square root of -27 with some algebra. You'll find that that ends up being 3 plus or minus 3i square roots of 3. And then that's divided by 2. So if I consider all 3 square roots here, the first root that we find comes from that original factor x plus 3. So we have a solution of -3, which is going to solve that to be equal to 0. And then we've got the other 2, which are in that plus and minus root. So that would be, first one would be 3 plus 3i square roots of 3 over 2. And then the last one would be 3 minus 3i square roots of 3 over 2. So those are your 3 cube roots. All right. And for time here, I think I'll probably, I can certainly make a little video right after class here if you would like to have that on YouTube for one more example with a cube root. And so I'll try to make that video today and post that. And then I'll just go through a case where we're finding really a fourth root of an equation here. So this is kind of going back to algebra again, with some complex roots, but I'll finish with this problem, and then I'll definitely send a video out for a second problem with a cube root. So let's consider how we would work this equation here. This is just going to be an equation that's going to involve some complex solutions. So one thing that we see here is this is kind of in a quadratic form, but we do have a x to the fourth and an x squared. So what would be one way I could manipulate this to get it down in terms of powers? How could I reduce those powers without, necessarily changing the whole problem? Okay, factor. Okay, would be one thing. Consider how we could factor. I don't know if this is going to factor cleanly. I would like this to have, at most a squared power in it. So one way I could get around this fourth power for the time being is considering a u substitution. So we could say, put a u substitution variable in to this equation to start out, and call that u substitution x squared. So if I have u equals x squared, that would mean u squared is equal to x to the fourth. So those would be my substitution variables that I could use to simplify this equation down to a quadratic. So this is kind of an old algebra technique, but it can come in handy with these fourth roots. So I have really here u squared minus 2u plus 2 equals 0. So that's my new equation I'd like to solve. And looking at this new equation, the u equation, this still doesn't look like it's going to be able to factor. So I think I do still need to go through the quadratic formula one more time. So if I have my quadratic formula, I don't write it down again on the side. In this case, we'll have a u is equal to negative b plus or minus the square root of b squared minus 4ac all over the way. And so we'll try to work that out with the u equation here. So we have a 1 as our a, negative 2, and 2 as our c. So I'll fill this in here. Negative b is going to be negative 2, which will just be a 2. Plus or minus, we'll have the square root of b, which is negative 2 squared, minus 4. A is still 1, and then c is a positive 2. All over 2 times 1, which is, again, just 2. So if we consider all the business in the square root here, what value are we going to get inside of that square root when we simplify? Uh, 4 minus, looks like 8. Yep, we've got negative 4 in the square root. Negative 4 over 2. How could I rewrite the square root of negative 4? What is that written as? That's 2i. Excellent. Yep, Kevin, you got it. 2i. And then over 2. So what we have here, this is really 1 plus or minus I. Okay? So this is our u. So if that is our u, let's consider what we have. So u is 1 plus or minus I. And so if I considered back to my regular substitution, or the original substitution was u equals x squared. So if this is equal to x squared, I'd actually want to go out and solve for x. I can do one more thing to solve for x, and that would be just to take a square root of both sides. So if I take a square root of both sides to find my actual solutions for x, not just u, this is what we'll get. We'll get x is equal to, well, the plus or minus square root. And we want plus or minus the square root of 1 plus or minus I. That looks kind of crazy, but there's really just 4 solutions there. That's exactly 4 solutions. And let's write those out just to make sure that we're clear with kind of all 4 solutions that we're actually getting. Okay? So we'll write these out one by one. So the first thing we could do is just the square root of 1 plus I. That's one of the solutions. We've got the square root of 1 minus I. That's a second solution that comes out of this. We could write this as negative square root of 1i. And then the last combination would be negative negative, which is negative on the outside and negative on the inside. So those are all of the roots, 4 cube roots, that we would get for the solution for that problem.